Lab 3, Black Hole. The purpose of the lab was to generate a unique star trajectory based off of an individual email address and analyze the star's motion to find the net force on the star for all points in the dataset, then use these results to estimate the mass of the black hole in the model. There were three major physics principles involved in this lab. The first one is the momentum principle, which states that the rate of change of momentum is equal to the product of the net force and the change in time. This can be rearranged to show that the net force is equal to the change in momentum over the change in time. The universal law of gravitation states that the force of gravity is the result of the universal gravitation constant times the mass of the first object and the mass of the second object all over the magnitude of the distance squared. For the purpose of this lab, we will be solving for the mass of the black hole, which is mass 2 in this case, so the equation has been rearranged to represent this. Finally, parallel and perpendicular forces will occur when an object is either speeding up or slowing down, or moving along a curved path. The parallel component of the net force is for when an object is speeding up or slowing down. This is equal to the parallel component of the rate of change of a momentum, which is equivalent to the change in the magnitude of momentum over time times the direction of the momentum. The perpendicular component of the force is for when an object is moving in a curving motion and is equal to the perpendicular component of the rate of change of momentum over time, which is equivalent to the change in the direction of the momentum over time times the magnitude of the momentum. Using the Lab 3 starter code, I began to make necessary changes to be able to find the correct mass of the black hole. I started by updating my email and the star's mass. Then I updated delta t to be equal to the amount of seconds in one day, which is equal to 86,400 seconds. The second while loop iterates over the data values and calculates the initial and final velocities and momentum, which is then used to find the change in velocity and momentum. It is important to change the initial and final momentum to reflect that they are equal to the mass times the initial velocity and the mass times the final velocity, respectively. dp dt was found by using the definition of the rate of change in momentum. Fnet was then set equal to dp dt based on the momentum principle. The parallel component of change in momentum was found by taking the product of the change in magnitude of momentum and the direction. The perpendicular component of the momentum was found by subtracting the parallel component from the total rate of change of momentum. The net parallel force was set equal to the parallel component of the momentum, and the net perpendicular force was set equal to the perpendicular component, both based on Newton's second law. Finally, the next step was the calculation to find the unknown mass of the black hole. I first set r to be the distance the star was from the black hole, and then found the mass of the black hole by multiplying the magnitude of Fnet by 2r and dividing that by the gravitational constant times the mass of the star. I also updated the arrows to show the different components of Fnet acting on the system. Here you can see the output when the code is run. The orange arrow shows Fnet, while the blue arrow shows the parallel component of Fnet, and the pink arrow shows the perpendicular component of Fnet. The results of the model show the mass along with the magnitudes Fnet and its parallel and perpendicular components. The first question asks us to compare the parallel and perpendicular components of the net force to the parallel and perpendicular components of the rate of change of momentum. As we can see in the first equation, the rate of change of the magnitude of momentum is equal to Fnet parallel based on the momentum principle. The magnitude can only be changed if there is a force component along the path the object travels. The second equation takes the rate of change of the direction of momentum and equates it to Fnet perpendicular, also based on the momentum principle. The direction of the object only changes if there is a force component perpendicular to the path the object travels. Another question arises asking us to imagine that the black hole we just found was replaced with a new black hole with a different mass. Assuming the motion of the star stayed the same, could we determine the mass of the new black hole if the motion is only affected by the gravitational force of the black hole? The answer simply is no. It would not be possible to find the mass because the position value is the same, therefore the magnitude of the position is the same, meaning the velocity, momentum, and net force would also be the same. So when we input the values into the rearranged equation, we would still yield the same mass value for the black hole. Thank you for watching my video.